All right, good morning, everyone. Hello, hello. Thank you for joining us today for St. Louis University's Introduce a Girl to Engineering Day virtual field trip. While we would have loved to have you in person for this event, we are glad that we can at least connect with you virtually today. This is the first ever virtual field trip that we're hosting with hands-on activities. So thank you for being a part of this groundbreaking endeavor. This event has been made possible through the American Association of University Women, St. Louis University, and our presenters today. We have a great itinerary of engineering faculty, current students, and hands-on activities for you through this webinar today. And we hope that you will be able to connect with and find inspiration from each of these sessions. My name is Amy Price, and I'm the outreach coordinator for our engineering programs. I'll serve as the webinar host today as we move from one session to the next. All sessions today will be hosted in this webinar space. We will be recording the webinar today, and that will be posted to our YouTube page, youtube.com/sluparks in the coming days. If at any point you have technical difficulties, we recommend first logging out and logging back into the webinar with the link provided by email. And if other issues persist, you can email parksevents@slu.edu and we'll provide what assistance we can. As you're going to learn today, the engineering industry offers a multitude of opportunities and careers. All of the professionals and students you'll meet during this event are excited to introduce you to what they do in their careers and their studies, and maybe it'll help you find your passion as well. In total, St. Louis University offers engineering programs in aerospace, biomedical, civil, computer, electrical, and mechanical engineering. We'll be highlighting several of these programs throughout the event today. Before we jump into our day though, I'm going to quickly go through some of the items you might want to have on hand for our activities. First, the Water Institute will be presenting a group activity. Students in groups of about 4 will work together to build a water filter. So for that activity, each group will need a water bottle with the top cut off, and holes poked in the cap, some pebbles, sand, a clear plastic cup, a notebook and a pen, a timer. So I will use my phone for this, or you can count the seconds on a clock, a ruler, and a Sharpie or a marker. Teachers or facilitators, you'll want to have the contaminated water mixed in a pitcher or other container before this activity begins. The next activity will be from our Chrome lab. So for that, each student is going to need a robot kit, one of these, a AA battery, and access to a Phillips head screwdriver. So I'll write this. And then finally, for our biomedical engineering session, you will either want a pre-made activity kit like this, or you can build your own kit with access to items like cardstock, rubber bands, straws, plastic spoons, dowel rods, string, paper clips, a medical glove, pipe cleaners, tape, glue, scissors, or a marker. So any combination of those items will work for that activity that they will explain during their session. So through each session, you will receive instructions about what to do with these items. Just for now, please keep them near you for easy access. Our facilitators will prompt you when it's time to use them. If at any point during these sessions you have a question about the content, a teacher or facilitator may submit those to the Q&A feature or the chat function. Time might not always allow, but if it does, we'll get to questions as best we can. We'll also try to build breaks in where we can, but if you do need to step away, please remember that you will have access to this recording later. So now it is time to get going for the day, and to get us started, I'd like to introduce biomedical engineering student Ingrid, and she's going to walk us through a presentation of just what engineering is, and she'll provide us some base knowledge for our sessions today. So Ingrid, when you are ready, it is all yours.
I don't know if anyone can see or hear me.
Yeah, you should be good.
Okay, great. Perfect. Yeah. So I am Ingrid. I'm a senior biomedical engineering student at St. Louis University, and I'm going to start sharing my screen so I can talk a little bit about what engineering actually is. So if you'll give me a sec to get started, we are going to, I'm going to move this out of the way. Alrighty, here we go. So what is engineering? So like the definition of engineering, it's a little bit scary. So it says the application of scientific and mathematical principles to practical ends, such as the design, manufacture, and operation of efficient and economical structures, machines, processes, and systems. So what that really means is that engineers use science to fix the world's problems. And there's a little bit of a disconnect there, but we can get to that later. So what do engineers actually do? So we create things that perform a specific function, like a bridge or a pacemaker or an airplane. And we do that using what we know about math and science. So engineers create technology like cell phones and computers or machines like MRIs and trains. And we do systems like highways and power grids that make the world a better place and keep things running. So there are a lot of different types of engineers, but we all share a love of math and science and the need to make our ideas a reality. And that's a big thing about being an engineer. So engineering, it's for the driven and the curious. It's all about critical thinking and applying concepts that are kind of more abstract to a real world problem to fix something. So engineering ends up being the perfect combination of learning and doing. People become engineers because they love learning about how the world works, but they also want to make a difference. So because of what we do and the kind of physical nature of it, we end up shaping the world we live in. So as an engineer, you kind of get to decide what the future holds, which is really fun. So you're building the cities of tomorrow and you're designing medical devices and you're creating all of this technology that the world needs. So as an engineer, you end up having a direct impact on the world around you, and you're at the forefront of a lot of really cool innovation. You actually don't need prior experience to be in an engineering program and getting an engineering degree. Like you don't need to have taken calculus or coding already. And that's like really something that I feel like not a lot of people know about engineering. Like I came into engineering with zero prior experience. I never took a coding class. I didn't have a super advanced math program. I wasn't in robotics club. Like I wasn't like what people would typically think of as like an engineer. And you don't need that background to be successful in college and as an engineering student, and then like later in your life as a professional. So don't let a lack of prior experience keep you from shooting your shot at something that you might find is like your passion. So like the point of an engineering degree is actually to learn how to be an engineer. Like no one expects you to be an engineer from the get-go. You don't need that prior experience to be successful. And you, as you go through college learning about it, you kind of get taught the concepts you need to know, and then it kind of shapes the way you think about things. So you find yourself becoming more and more of an engineer as you go, and it's actually like really fun looking back on it. So you already have the skills you need. The thing that's really sets engineers apart is the way of thinking, not so much like what you know. So you have this really strong desire to know like the why and the how things work. So it's like, okay, yeah, I get that this machine does this, but like, why does it do it? And like, how does it do it? And you are passionate about solving problems. So it's like, okay, this is an issue. How can I fix it? And how can I fix it in a way that hasn't been tried yet? And you have a drive to like get the job done, where it's like, okay, this is a problem. We need to fix it. How can we fix it as soon as we can and in the best way possible? We're people of action. We like to do things. We're doers. We don't just sit around in like a cubicle. You're out there and you're like working to fix things. So as an engineer, you're seeing patterns that fit together and you piece them together and you solve a complex and challenging problem. and you end up surprising yourself with your own ingenuity. And it's a pretty fun little adventure. So engineering has a ton of different disciplines. Like you can be an engineer in so many different fields. There's aerospace, so that's like airplanes and rockets and satellites. There's biomedical, so they can work on like prosthetics or MRIs or pacemakers. And then you have civils, which do kind of like city planning and roads and bridges. And then you have computer engineers who deal with computers. And then you've got mechanical engineers, and they kind of deal with like what you would classically think of as engineering with the machinery and stuff. And you have electrical engineers too, and they deal with stuff like power systems and power grids and wiring and small scale electronics and large scale electronics. So there's a lot of variety there. So engineering is everywhere, and engineers are everywhere. Like you need engineers in pretty much every field. So you see engineers kind of working for major engineering firms where like they do engineering, like that is the whole business. But a lot of times engineers end up in other places too. So they end up working in hospitals and in medicine or in architecture or in various areas of industry. And it's really, really neat to see kind of where people end up. They work about just anywhere you can imagine, there's probably an engineer somewhere hiding. So there are so many career options. Like since you can be just about anywhere, you have all of these career options open up to you. So you could be working in industry. So you're working in like research and development for new technologies. You could be in manufacturing. So like you're running factories and plants, entrepreneurship. So you could start your own business, contracting. So you could maybe consult for a larger firm, quality control. So like you're making sure that everything in production is adequate and things are working the way they need to work. And when they don't, you go back to the drawing board to kind of fix it. And management. So you can be in a leadership position where you're running major engineering projects. So it's a good time. So kind of to sum it all up, engineering gives you options. So there are tons of different disciplines that work with engineers. Engineers work with other people. Because we have kind of a shared background, you can move into different engineering positions and jobs. So like say you started in like research and development, and you're like, actually, I think I would be better in management. So you can swap in and out within engineering, but then you also end up working with people who aren't engineers, which is kind of exciting. There's a lot of innovation. So you have all of these new technologies being created around you, and you're contributing to that. And it is like, it's wild. It's so fascinating. You get a different perspective when you're an engineer. Like you just see the world differently. And I don't know why, but like we just see it differently. And so that is like a really unique thing about it. You end up with real world skills super early on. There are tons of possibilities, and like you are striving for personal excellence and you reach it as an engineer. You really push yourself, and it's a really great thing. So that is it for me. I think Amy's going to take the floor. So
Ingrid, thank you so much. I hope everybody learned a little bit about just what engineering is. Ingrid, before you go, really quick, could you share with us what your personal career goal or career goals are?
Yeah, so I am a senior, which means I have to leave and go into the real world now. So for me, as a biomedical engineer, I really like tissue engineering, which is when we try and recreate organs by engineering them, and then you can kind of implant them into people who have like lost an organ or a damaged organ. Skin grafting is kind of like the big field where you're kind of replacing skin. I really enjoy working in a lab. So my career goal is to be the leader of my own lab in a research hospital, because I think it'd be really neat to be kind of on the cutting edge for that sort of like translational technology where like I'm directly interfacing with doctors and patients to say, okay, you have a problem. What do you need? And then I can go back to my lab and I can kind of make what they need, and then they get it in a pretty timely fashion. So that's kind of where I'm headed.
That sounds amazing. I know you're going to change lots of lives, and Yeah, you'll change the world that way. So thanks so much, Ingrid. It was great.
Yeah.
Great having you present. We are now going to head to the Water Institute with Dr. Cox, Sophie, and Rachel. So they're going to talk a little bit about what they do at SLU's Water Institute and lead us in our first activity. So you guys can take it away.
Thanks, Amy. Thanks for that introduction. My name is Amanda Cox, and I'm an associate professor of civil engineering at St. Louis University. I'm also the director of the Water Institute at St. Louis University. So I'm going to share with you guys a little bit initially about what civil engineering is, and then talk about my specific area of expertise. And then I'll talk just very briefly about the Water Institute, which is really quite exciting. And then Sophie has an exciting water filtration activity that we're going to do. We're currently located in the building that you see. It's our new interdisciplinary science and engineering building. And the Water Institute has 3 large laboratories in the basement. All right, there we go. So what is civil engineering? Ingrid said a little bit about it, but we can think of it as the design and construction of infrastructure, including roads, bridges, canals, and we also sometimes hear this called the built environment. Civil engineering is one of the broadest engineering disciplines. You can see there's 6 different key areas. And what's really quite interesting about civil engineering is we use probably the broadest spectrum of science applications. So we go from physics, but we also have environmental and biological applications as well. So structural engineering is one of the more common areas that people think of for civil engineering, and that includes bridges and buildings. Transportation engineers deal with designing and constructing road systems and traffic signals. Also, that expands to airports and trains as well. Environmental engineering is the one discipline that also, in civil engineering, that also includes biological and chemical processes, as well as physical processes or physics-based engineering applications. And environmental engineering, some common applications are drinking water treatment and wastewater treatment, as well as maybe removing contaminants from soils. And of course, those, I said, use biological and chemical applications as well. Geotechnical engineering is a field that most people aren't very familiar with, but it deals with the engineering using soils material. And so with this includes foundations for structures, or maybe stabilizing slopes that are prone to sliding. Water resources engineering, this is my area of expertise. It deals with the flow and conveyance of water. These are our civil engineering faculty here at St. Louis University, and you can see we cover that broad range of specialization within civil engineering. And before I go on to talk about some of my specific research projects, I wanted to give a shout out for our annual design competition called Billiken Beams. And this is a design competition that's held annually. It'll be held here on SLU's campus, April 2nd. And teams usually form in the fall semester. So if you guys are interested at all in participating in this competition, I recommend that you check that out online. So I'll talk now more a little bit about my main area of expertise. So hydraulic engineering is even a subdiscipline within water resources engineering, and it deals with the flow, conveyance, and storage of water. And we can characterize those into 2 main groups: surface water hydraulics, and these include rivers, urban drainage, dams, maybe flood control, channel navigation, and these are all flows that are driven by gravity. The other area of hydraulic engineering we can call as closed conduits, and that includes things like the water distribution systems that we have, as well as pumping water for irrigation and agricultural purposes. And so that one is not gravity driven, those are driven by pumps. So I like to highlight that in my area of civil engineering, and really across all areas of engineering, we use a lot of technology. So we use computer modeling. You can see an example of a computer model of a dam spillway on the right. We use a lot what's called geographical information systems. And so this allows us to use geospatial data, areas and elevations and other information about the ground and the environment that we need for our designs and our analysis. I've also used remote sensing. The image on the left shows a way that we can estimate the amount of sediment that's in the Mississippi River. This is the confluence of the Missouri and Mississippi River. And we can estimate the amount of suspended sediment concentration in those areas using satellite imagery. So that was really exciting. That was a project from a few years back. We're currently using machine learning and artificial intelligence to look at how reservoirs fill with sediment over time. And then we also use a lot of laser acoustic instruments to measure various properties of flow and sediment transport. So one of my projects is funded by the National Science Foundation, and it is a project where I'm collaborating with several other universities, and we're developing an online platform for what's called river morphology data. So information about river shape and form and material. Another project that I wanted to highlight is a project that's funded by the U.S. Army Corps of Engineers, and it's also a collaborative project. And we are developing a computer tool that can do long-term forecasting of river channels. So it's a physics-based model, but channels really have a lot of complexity. And so in addition to the driving physics of the model, we have different empirical components that will model the unique, more challenging behaviors of rivers that can be difficult to model using physics. And then the last thing that I wanted to highlight before we get onto our activity is our new Water Institute. The name is Water Access, Technology, Environment, and Resources. And this institute has been around almost 2 years here at St. Louis University. It's an interdisciplinary institute that focuses on 3 areas. So water in the built environment, aquatic ecosystems, and social justice issues related to water. The Water Institute, being broad and including factors like social justice, it really tries to address some of the most critical and persistent water challenges that we have using that interdisciplinary approach. So we know that we have to have solutions that work both from the scientific perspective, from an engineering perspective, but from an economics perspective or a public health or social justice, or even the policies that we have to put in place to enable some of these engineering designs or solutions are important to how we move forward with those challenges. And then of course, we're located here at the confluence of the Mississippi and Missouri River, so it's an excellent location for our institute. With that, I'll hand it over to Sophie Liang. She is our laboratory technician here at the Water Institute, and she has her degrees in environmental engineering, and she's going to lead us in the water filtration activity.
Can everyone see the slides, and can anyone hear me?
Yeah, hi Sophie, you're all good.
Thank you. Hi everyone, I'm Sophie. Thank you, Amanda, for your introduction. I have a master's degree from environmental engineering from Iowa State University, and now I'm the lab technician at Water Institute at St. Louis University. So one major job for environmental engineers can do is to build and design water treatment plant like this. So this is a typical demonstration of how water treatment plant works to take water from lake or groundwater and treat those water with different steps into the water from our tap, which is drinkable and safe for us to consume. Typically, if we take water from a lake, we have to remove the large particles first, and then we go through some coagulation, flocculation, and then we go through the sand filtration system to remove fine particle and even the harmful chemicals, harmful compounds. And then we can go through some better treatment process, and then we have the water that's able to safe for people to drink. So I circled out the sand filtration part, and excuse me, I myself actually built a lab scale sand filtration system during my master's research program. It looks like this, and we're going to build something just like this, but smaller. So from this picture, you can see I have 4 tubes. I used PVC pipes to assemble with caps, and then I added gravel and sand and granular activated carbon to make as material to treat my water. I took water from a river, which is really turbid with a lot of bacteria and sediment. And I also added a harmful compound, which is microcystins, into my river water input. And the results after the sand filtration process, which is from the down from down here, and after the sand filtration, my water were detected. They are not as qualified as drinkable, but most of the turbidity sediments and the harmful compounds were actually removed just by a simple sand filtration like this. So today we're going to make something really simple and real quick. And even with something this simple, you can see a significant change. Hopefully you can see a significant change between the untreated water and the treated water. So now I will just go through again with the material we're gonna need. First, we will need the dirty water, which will be prepared by your teachers. Teachers will add the soil into clean tap water and mix it into this dirty water. Yes, and we will also need this plastic bottle. The bottom of it is cut off, but we're gonna use it upside down, like Rachel is showing you in the video, if you can see. And keep the cap closed, because when you put the material in, you want to make sure they stay in until you open it. And you will have a ruler to measure how much water and how much of each kind of material you put in the plastic bottle. And you will have a clear cup to contain the water that's being treated after they go through the filter. The material includes gravel and sand. Yes, you should have 2 bags of each. You should have 1 bag of each. And then you will need a timer. I recommend you use your phone, or you can count on your clock. Okay, let's get started. So first of all, on your notebook, I would like you to write down this table. This is all the parameters we're gonna have you to record when you build your own filter. And after that, we're gonna do a simple calculation, which is gonna be fun, and also help you determine how good performed your filter is. So the first column, you have the depths of gravel, and we're gonna record also depths of sand, and the time it took to filter all the water added. This, you will need your timer to do this, and the volume of water. We're gonna do a simple calculation with this for this, And the flow rate is something we will calculate at the end. Oh. I'll give 1 more minute until we move on to the actual steps. Okay, I hope everybody have write this down. If you haven't, you can talk to your partner, and then hopefully we have it on your notebook already. So the first step is to make sure the cap of water bottle is on. Everybody have it on. Great. The second step is to add the gravel into the bottle. Just pour as much you want as in it, and make sure, I just want to remind you that the gravel we provided is not for you to, the amount you don't need to add all of them in there, just add the amount that you think will be best for the filter.
Hey, Sophie, I'm just jumping in, but each group can, because they're deciding how much gravel they're going to put in across a classroom, everyone's filter is going to look different, correct?
Yes.
Okay, cool.
And after you do that, use your ruler to measure how deep is that gravel you just added, and write it down on your notebook in that table you just recorded. Okay, I see Rachel and Amanda already finished, so let's move on to the next step. Now,
Hey, Sophie,
yes.
we have a quick question. Would you like us to measure in inches or centimeters?
That doesn't really matter. Let's do centimeters just to make sure everybody's the same.
Great, thank you.
Yeah, everybody, let's do just centimeters. Good. So next step is to add sand and measure the depth of the sand.
And Sophie, while everybody is adding sand, is it important to leave some space at the top of the bottle?
Yes, we don't want to fill that all to the top of the bottle because we will add the dirty water in your bottle. So leave some room so we can have enough space for the water.
Okay, thank you.
Thank you for clarification. Yeah, the depth of sand should be from the top of the gravel to the top of the sand. Richard is doing a good job. Okay, now next step is for teachers please mix the tap water with the dirt and make sure they're mixed well. And before you pour that dirty water into each group, make sure you keep mixing it so everybody have the same quality of dirty water. Thank you. Do you is that water bottle has a hole on the cap of the cap in the middle of the cap?
Yes, each water bottle has a series of small holes across the cap.
That's great. So now when you pour the dirty water into the sand filter, you don't want the filter to be dripping right away because we need to measure how long it takes to filter the water. So you need to use your finger thumb. Just try to block all the holes so the water doesn't come out right away. And now it's for teachers to add the mixed dirty water into each group's sand filter. That water is really bad.
And while teachers are going around and putting water in everyone's filters, as best as each group is able, they should keep their filter capped, correct?
Yes, keep the filter capped, use your finger. It seems kind of difficult. So once you have your water already, don't wait, just to measure the depth of the dirty water just added. And then write it down on your notebook. And then you don't need to wait for the rest of team. You can release the bottle of the filter and then make sure you start recording when you release it. So you know how long it takes for the water to go through. Teacher, please don't discard the leftover of that dirty water so we have something to compare to.
And classes, if you have a teacher or facilitator able to type into the chat and let us know when you're done pouring the water through all of your group's filters, that'll give us an indication we're ready to move on. Thank you.
Okay. We can see that Water Institute team is already finished. The before and after is significant different. While we're waiting for the rest of the groups, you can think about name your group some exciting names, and feel free to write it down on your cup with the treated water. Water Institute, what's name? What the name we're gonna give us? I'll give 1 more minute and then we'll move on to the calculation. Okay, hopefully most of you have finished. So you should have all the numbers here. If you have noticed, the volume of water, we don't really know yet. We only have the depth of water. The volume of water we need to do a calculation. I think you probably have had this math class already. So the volume, to measure the volume of water, we want to know the diameter of the bottle because we have the depth, which is the height of the volume. And then if you use your ruler, measure the diameter of your sand filter, which is that plastic bottle. And then you use that number divided by 2. That would be your radius. Okay, Water Institute have that number. And now you use the square of the radius and times pi. That should be the area, surface area of your water volume. And then use that area times the depth of water. That would be the volume of water you added. I don't have that equation on my slides. I apologize for that. So if it's possible, could teacher help students demonstrate this equation? This equation to calculate the volume of water.
Sophie, we just put that equation in the chat. So if teachers didn't quite get that when you were describing it, it's in the chat.
Thank you.
Sophie, the height is in, what are the units here? The height is in centimeters and the radius is in centimeters.
Yes.
And then what's that conversion between, oh, I don't know. What's the conversion between cubic centimeters and milliliters? We want it in I just have to look it up, but I don't have it with me.
Oh, it's
Centimeter
actually,
equals 1 milliliter.
Okay, great. 1 cubic centimeter equals 1 milliliter. I thought so, but we've confirmed that. So as long as they're putting their units in centimeters, we'll get milliliters per second. Okay,
yes,
great, thanks.
all your units are centimeters. And the unit of the volume is centimeter cube centimeter. And that's equal to the milliliters. I see that Water Institute is done. Good. I'll maybe give 1 more minute. And then with the volume, now we can calculate the flow rate. You just simply use the volume divided by time. The unit of time is second. And then you got your flow meter, which is milliliters over second. We got our calculation. Our flow rate is 3.2 milliliter over second. Thank you.
Hey, Sophie, as everyone is calculating, is there a reason you would want a slower or quicker flow rate of a filter?
Yeah, in an engineering world, we want efficiency, but efficiency is not just about the flow rate. It's not just about how quick you get things done. You also want to have a well-treated water. So I can see your filtered water, but I can assume that some of your filtered water are better than some other teams, but you may have a slower flow rate. So what engineers do is actually find the balance to have the maximum best flow rate, which is most fast flow rate, will also give good quality treated water. So there's always a balance.
Thank you.
Mhm. Okay, I think most of you should be ready. Now we move on to our discussion section. Let's talk about our results. So what first question I want you to think about is, what are the parameters that affect the time it takes to filter your water? Any volunteers?
If any classes would like to submit their observations or comments, you can do that through the chat. Or if this is just a discussion that you want to have amongst your classmates right now or later, that works as well.
Yeah.
Maybe the Water Institute team has some observations to share.
Hey, everyone. Hope you're enjoying the activity. So Dr. Cox and I were just looking at our water, and we were talking about the different proportions of gravel versus sand that we use in our filter. And so while you can see there's a noticeable difference in the turbidity of the water, there's obviously still some turbidity in this water. And so we started to discuss if we used maybe more sand or more gravel and sand, or maybe even a finer sand, if those would have impacts on the filtration effectiveness. Anything you want to add?
No, that was exactly what we were discussing. Thanks, Rachel.
Mm-hmm.
Thanks, Rachel and Amanda. I think that's really good answers. In water treatment plants, there's definitely the material of the filter material that need to be considered. Like I mentioned, when I was building my sand filter, I used granular activated carbon, which is kind of like sand, but it has better absorption function. So that helped me remove even harmful compounds that I was adding, and also help remove the bacteria and some other fine compounds. So that's good answer. Let's move on to the second question. What are the parameters that affect the cleanness of the outlet water? I think these two questions are pretty similar to each other. Like I said, when I was answering Amy's question, there's a balance to make the sand filter work faster, but also work better in providing cleaner and safer water for us to drink. So the third question is to help you review what could you have done differently to get a better filtration performance, which is faster and cleaner outlet water. So Rachel actually already gave a really good answer. We might want to find finer sand and maybe even add more sand and more gravel and see how it goes. And I'm sure you have more answers.
If any groups want to share their flow rates or any of their thoughts around how much sand versus how much gravel they used in the chat, it would be cool to see some of the differences in your designs as well.
Yeah. I think once you finish your calculation, you can even write the flow rate on your cup and then just have all of the groups cap together line up, and you can have a visual compare between the results between it among all the groups in your class. And then also discuss with each other what they did. Why is their treated water looks cleaner than yours? Or why is yours faster? There's a lot of things you can compare and discuss. It would be awesome if some of you can line up your treated water all together and then take a picture and share with us. We would love to see your results. And you don't have to send us the picture now, but we would like to hear from you even after this section.
All right, I think we're about out of time. Does anybody have any questions before we move on to the next activity? All right, well, thanks so much for having us this morning, and we hope you had a good time learning about water filtration.
Hey, thank you so much, Water Institute. We so enjoyed this activity. For our students and classes that are logged in, if you have additional thoughts on this, feel free to email them to us afterwards. We would love to know how your filters worked, if you were able to calculate all the various parameters of them. And we would love to know what you learned from this as well. This is one of the downsides of our webinar, is that we know you guys are working hard on the other side of the screen, but we can't see you. So we would love if you'd be able to share. Again, thank you to the Water Institute. We are going to take,
Thanks, everyone.
Thank you. Thank you. We're going to take a 1 minute break right now. And now would be a good time to dispose of any used materials from that activity. We found that the plastic bag that either your pebbles or sand came in is a good container to dump everything out into. Water, you might want to save that to compare groups one to the next. And we'll give you about a minute now to switch everything over. And next you will want to grab your robot kit and your battery and get your hands on a screwdriver. And while you are doing that, I'm going to bring our next presenters over. So sit tight for just a second. Thanks. All right, just to keep things moving, we are sure that you have some activity going on in front of you right now as you're switching out activities. Hopefully we can do that and also listen to our next presenters at the same time. We've got a lot to pack into this session, so we are super excited to get started. Next up are presenters from our Chrome lab at St. Louis University and our mechanical engineering program. First to present will be Dr. Gorlewicz. I will let her introduce herself and all of the fun things going on in their lab. And you guys can take it from here. Thanks so much.
Awesome. Thanks, Amy, and welcome everybody. We're so glad that you're here today. My name is Jenna Gorlewicz. I'm an associate professor in mechanical engineering here at SLU. I'm also the associate dean for research and innovation over our School of Science and Engineering. So incredibly excited that all of you are here and participating. And I just wanted to say a few words about my own path into engineering, just as a sort of an anecdotal story. So I started out in undergrad as a biology major. I was planning to go to medical school. I think it was in the middle of my sophomore year. And then for reasons that still aren't quite clear to me, I switched. I loved biology. I loved the idea of going to medical school. I was kind of thinking I maybe didn't want to go to school for that long. So I switched over into mechanical engineering, primarily because it was one of the broadest disciplines and I didn't quite know what I wanted to do. But I knew that I wanted to continue to work on something that was going to provide me a career pathway to helping people. And I switched over to mechanical engineering. I started getting into robotics, and then I went on to graduate school so that I could work on robotic systems, particularly in medicine and also in education. So what you're going to see today in the Chrome lab is a culmination of lots of projects that spread across robotics, spread across medicine, spread across education. And I hope what you'll see is that engineering is indeed a career pathway by which you get to work with people. And so that is one of my most favorite things about looking back. I'm super glad I made the change into engineering. And I still have connections into the sciences with a lot of the research that we do. And I hope that you'll see that engineering is a pathway by which you can be involved with the communities that you care most about. So without further ado, I'm going to turn it over to Jen and Maya, and they're going to show you around the Chrome lab. Chrome stands for Collaborative Haptics, Robotics, and Mechatronics. And that's a lot of fancy words to say we make really cool things that with people that hopefully change the world. So Jen and Maya, over to you. Everyone else, enjoy the rest of your day.
Thank you, Jenna. So my name is Jen. This is Maya next to me. Hello. We're professionals that work in the Chrome lab. We're engineers, but we're two different kinds of engineers. So to begin with, before we start building the wonderful kits that you all have, is that we wanted to speak a little bit about our experience as engineers, how we got into it, why we like it, and then we'll just dive into the kit. To begin with, I never considered myself an engineer until I was probably in my mid-20s. I started out going into psychology. So my background is actually in psychology. I wanted to be a counselor. I really wanted to get involved like social justice wise and things like that. But as I sort of grew, I realized that there was an angle of psychology and sociology that I really enjoyed that nobody was really looking at. And it was the angle of technology. Sometimes when you think about engineering, you don't think about the people that end up having to use what engineers make. And I'm that person. So we call that human factors engineering, this blend of making things and making technology specifically for use by people. What we like to say here in the Chrome lab is like, it doesn't matter how great your piece of technology is if nobody can use it. So I focus on assistive technology, especially in education for non-traditional students. So students that maybe have a disability or students that maybe just need a little bit more to help them keep up with everybody else in their class. And what I really love about engineering is the fact that it's so broad. So like I said, Maya and I are two different kinds of engineers. I'm human factors, and Maya will tell you a little bit about her kind of engineering. But you know, thinking back to how I thought about engineering when I was in high school and when I was in undergrad. It was a very narrow view and I didn't really understand everything that engineers did. But I can safely say now, like looking back, if no matter what you want to do, whether you want to go and help people, you want to be a psychologist, you want to be a sociologist, you want to be a biologist, there's room in engineering for you. And it's not room that you have to carve out. It's already there. So I hope that you will all consider engineering in one capacity or another at one point in your life, because it's a very useful set of skills that you learn in engineering, and it's a very fun sort of space to work in. With that, I'll turn it over to Maya.
Hi, so I'm Maya. Jen said earlier, I also work here in the Chrome Lab. And like Jen said, I am a very different kind of engineer to the kind of engineer she is. I'm more traditional in the sense that I've kind of almost always been in engineering, bar a couple of days where I was not an engineering major in college, but I have always worked in what's called mechanical engineering. And it's one of the more basic forms of engineering. It's really broad, and so you can learn a lot about there's a lot of kind of applied physics, and a lot of how things work and why they work, especially in like machinery, and you also get a little bit into things like fluids. It's very broad branch of engineering. It's one of my favorite reasons, and it's why I chose that particular discipline. It's because it allows you to do so many things. I've worked in automotive industry before. I've also, worked in things like education, as well as technology, and I currently work in robotics. But that's not even all that mechanical engineers do as well. There's, I know a lot of people who work in, I have friends who work all over. There's some who work in the cosmetics industry who are mechanical engineers. I have friends who work for an aerospace industry, and it's just very broad. You can do basically whatever you want or work in whatever industry you want. And it's one of my favorite parts about engineering. I kind of fell into it. I wasn't really planning to be an engineer. Whenever I left high school, I wasn't like, oh yes, I'm going to be the best engineer ever. I actually had plenty of other plans. I originally thought I was going to be an international business major. Like I said earlier, that kind of happened for 2 days. And then I said, you know what, let's give engineering a try. And I actually ended up really loving it and liking what I could do, and that I could actually build things to help people, because one of my favorite things is being creative. And that's something that a lot of people don't think about, but engineering really allows you to be creative and see what you can do with the world in front of you. It's just one of my favorite parts. And with that, I think we'll start building the kits.
Yeah, let's go ahead and start building the kits. So if you haven't already taken them out of your wonderful box, that would be the time to do so. I will say one thing about the items in the box. Please feel free to remove the plastic on every single one of them. But there's a small bag of very small parts that you probably either want to use scissors to cut the top off of the bag, or just leave everything in the bag until we're ready to get them, just so that they don't get lost. And we'll go ahead and switch camera view so you can see what's on my desk. All right. So this is what we have. With our remaining time, we're going to go through how to build this beautiful, beautiful crab robot. If you haven't read what it actually does, is it's pretty cool. Let me see. Thank you. If you set it down after you turn it on, it wiggles a little bit in your hands, but if you set it down, it rolls away. But when it reaches an edge, other way. When it reaches an edge, it'll turn and not fall off. Thank you. Topsy-turvy. So this is what we're going to be building today. What Maya is going to do is Maya is going to read the instructions, and I'm going to make it in front of the camera. The first thing that we're going to do is we're going to read a listing of the parts that you should have in your kit, just so that when you start, you have everything that you possibly need.
All right. So first thing that you have is what's called the transparent cover. The first time I ever built this robot, I definitely thought it was just to hold the small pieces, but it's actually part of the robot. It goes over the top of the next part, which is the chassis. And that's basically the body of the crab. It holds most of the, electrical and mechanical components that make the crab work and function the way it does. So it has the wheels, it has the motor that drives them. It has gears, which in turn like move the arms eventually. And yeah, it's basically the core and the heart of what makes the robot function. Next, we have a bunch of little legs. There should be 8 of them in your kit. These are mostly for cosmetics. They make it what make the crab look like a crab. And then along a similar vein, there are 2 claws that go on the front. And those are really the main components that make up the crab robot. But we also have, unique components to put them together. So how do they fit together? How do they work? And that is in that really tiny bag that Jen showed earlier. That is everything from the antenna, which, looks like the crab's antenna, to screws, to gears, axles, which are what hold the gears in place, as well as terminal caps, which is how we keep the electrical wires going where they're supposed to go. So that's all the components. So I guess we'll get started building the robot. So
It's just a good thing to note that you will also need a Phillips head screwdriver. And if you don't know exactly what a Phillips head screwdriver is, undoubtedly you have seen one of these before. It has a star tip. So you know that commonly there's flathead screwdrivers and then star tip screwdrivers. You want the star tip screwdriver one. And then you'll also need 1 AA battery. Okay.
all right.
Tell me what to do.
Well, one other part that we missed. We also have the battery holder, which
yeah.
I forgot to mention. And it just holds the battery. And it also helps pull to the other components in place with the way that it's built. But
And this is the cap that goes on the battery.
the cap that goes on the battery. So, all right. The first thing you want to do is you want to get your chassis. And you are going to want to have it so that you turned, you got it this way, the right way. So that the area where the pinchers are supposed to go is facing away from you.
Okay, so here are the pinchers, if you can see them on the chassis. So they're facing away from me.
Yes. And so what you want to do is you want to grab some of both axles from out of the bag.
Oh, give me a second, they're really small. Okay, so an axle are these small bars. Let me see if I can't get it to focus in on them. They have nothing on them. They're just two small bars, metal bars.
So you'll take those bars and there'll be a couple of holes right behind the gears.
So right here.
Yep. And you want to place those in to those holes.
Okay.
They kind of just slide in.
So there's 2 holes right next to the motor and next to the gear wheel. You're gonna put one in each of these 2 holes back here. Let me see if I can actually even bring it closer. So I'm gonna use the screwdriver to point to them. So there's a hole here where an axle should go, and then a hole here where an axle should go. And we're gonna put them both in there. We're just gonna slot them in. So one goes there, and one goes there.
All right. And then you're going to take both of the gears.
So the gears are in the
The
bag.
gears with a little white,
So they're these things.
gears in the bag. They're kind of a little hard to see. There you go.
Yeah, I'm trying to get my camera to focus, but it wants to be ornery today. But they're the only white things in this bag. So we're going to use both of them.
Yep, you're going to take both of them. And you're going to slide one over each of the axles.
Okay. So I'm going to do it on the big gear first. Just going to slide that in. It falls right down. I'm going to slide the other one right next to it. Okay. So both of the gears are now resting on those axles.
And so it should be so that the one that's closest to the big wheel touches, well, so the gear that you just put in that touches the big wheel.
Mm-hmm.
And then the one that touches it's the one right next to it, touches what's called, it's usually called a worm gear, which is the like spiral kind of gear that is connected to the motor. And so why this is important is because that motor will turn and will then move all of the other gears with it. So the motor from the rotation of the motor leads the rotation of the gears, which actually turns or makes the robot move. So the next, you're going to take your battery holder and you're going to place it on top of the chassis. So if you turn the battery holder over, there's a bunch of little holes. And those holes slot over the axles that you just put on the robot, as well as the two on the sides fit over I guess the two big holes that are, or the two big pillars that are on the side.
Okay, so flip this over. Now that
Turn
we're
it
done
around.
looking at the bottom, I'm gonna turn it around. Okay, and you'll see that there's two big holes on the side of this casing. Those are gonna go atop of these. Okay, so I'm gonna place it right over it. Yeah.
And you want to make sure that the axles that you put in fall into those holes that are on the back.
Ah, I see. Okay, so we're gonna have to line these holes up with these axles that we just put in. So that's probably gonna be the first thing that I do to try to do is just put those in. Okay. All right, so it actually slides in pretty easily once you're on top of them. Cool. Well, it would if I didn't lift it back up. Okay, let me try this again, and they go in there. Perfect. So it doesn't necessarily fit or rest on top of it perfectly. We'll have to screw it in. But don't worry, we're gonna screw it in.
This part is takes a little more time.
It's a little challenging.
Yeah, I was gonna say, when I built the robot that we showed off earlier, this was probably the most difficult part, was getting the battery case to align perfectly.
Goodness
the way
gracious.
it should. One thing that might help is, so there's two wires that hang off the side of the battery case, which are basically your positive and negative sides of your battery. You can like slide those up. You can push the wires up a little bit so that those wires don't try and force back down, which makes
That's very smart.
the battery case move on or move up.
Maybe. Did I get it? Oh, I think I got it. Okay. So this is how it rests. The battery casing is this right down here, and it's resting just across these two axle gear wheels.
All right. Well, the next thing you're gonna do is, we just mentioned the wires. You're gonna want to pull out the wires from underneath the motor.
Okay, I'm gonna use my screwdriver to do that. You can be a little bit rough with them. They're wires, they'll live. Okay. Should I pull the
Push them both. You'll want to pull them back both towards you,
back
because you'll see that there's these two holes that have metal rings around the top.
I'm actually gonna do this first. I'm gonna take off the battery casing, put back on my gears, and then I'm gonna preemptively take these wires and pull them back so that I don't have to do it when the battery casing is on there. And then I'm gonna put this back very gingerly. Okay, now it's back.
All right. And so you'll see that there are two red wires and there are two black wires.
Two red, two black.
The two red wires go together, the two black wires go together. It's usually a convention of electronics, so that your red wire is your power wire, which, is it your black wires are your ground wires. And so since they go together, you're going to want to electrically connect them. And so you don't have to do that in a complicated way. We have terminal caps for that. So what you'll want to do is take the two black terminal caps.
So the two black terminal caps are actually in this bag.
Are in the bag.
Oh, yep, we can slow down.
We can definitely slow down.
So we'll put these aside. Just let us know when you're ready.
And while we take a little pause, if there are any questions that you have for Maya or Jen about robotics or engineering in general, this might be a good time to ask those.
Yeah, I agree.
Can I ask you guys, what are some of the projects and research projects going on in the Chrome Lab that you guys are working on?
Well, Maya and I just finished up a big robotics project. If you want to talk a little bit about that, since you were the lead on it.
Sure. So this project was basically about, remote communication, is what we're doing right now. Sorry, see the bit of a question. The second key keeps getting stuck when the battery gets put on. What do I do?
Yeah, so it's something that you'll have to work with. It kept happening to me. If you remember, I couldn't get it to line up exactly correctly. And when I tried to adjust it, sometimes you pull out that axle with the gear on it. You just have to kind of gingerly put the battery casing over it to the best of your ability, such that it might like rest precariously on there until you screw in the stabilization pillars. Just keep working at it.
Yeah. I was gonna say, one thing that might actually make it easier is once you get the casing on there, we can take 2 screws and you can screw in the sides of the battery casing. Just make sure you pull out the wires from the motor before you do that.
Yep.
And that will make it a little bit easier to get that to work.
Boy, these screws are real small, let me tell you.
But back to Amy's question. So basically what this project was about remote communication, which we're doing right now. And it was about trying to figure out if there were ways that we could conduct handshakes remotely, and figuring out if we put these gloves on people, these wearable gloves that had different kinds of what's called haptic feedback on it. And that basically means it just had feedback that dealt with your sense of touch, how that would affect being able to conduct remote handshakes. If it made it better, if it made it worse, all kind of stuff like that. And that's just one small part of a big robotics project that we're working on. And it's pretty cool.
Yep, so that's what we've been sort of neck deep in recently, but elsewhere in the Chrome Lab, we've got some folks working on what we call wearable devices. So you can think of them for anywhere from like an Apple Watch to more experimental type devices that like go on the leg to like measure different like health related things and maybe give some feedback. So one of the coolest projects I think going on in the lab right now is the development of one of those wearable haptic devices or wearable devices that utilize touch sensations. So in the form of vibrations, in the form of skin stretches and squeezes to help deafblind individuals better communicate in a remote world. So if you're not familiar with the way that deafblind individuals have to communicate, they don't have hearing, they don't have sight. So they have to use touch and they use a special sort of sign language. And to help them communicate with other deafblind individuals or maybe other family members remotely. So if somebody isn't in the room with them, that's very difficult. To help them, we're trying to develop a haptic wearable sleeve that goes on their arm, their hand, their body, not their body, but their thigh, to help them sort of communicate with those individuals and get communication back from them. Otherwise, we have some projects going on in education right now. We're developing a device in conjunction with PhET Interactive simulations, if you've ever heard of them. they're really popular educational, like online simulation nonprofit. Lots of cool stuff there. Highly recommend just going there and playing with some of the simulations that they have. But we're working in conjunction with them to create a physical device for one of their simulations so that people can more more enjoyably interact with what the simulation is trying to teach. Because I'm sure you guys are all familiar with how boring online learning can be sometimes. And it's much better to have something in your hands that you can play with while you're learning. So we're helping develop a tool that allows you to do things with your hands while you're learning, basically.
All right, back to the robot.
Back to the robot.
So yeah, just make sure you have those two wires pulled out.
So these two wires.
Yep, and have them kind of grouped together. And then what we're gonna do is what I mentioned that makes this a little bit easier is we're gonna screw on that battery cap. You just have to make sure that those wires are out from under the motors first.
Yep.
Or else it's hard to get.
And just to be clear, you're gonna use just the regular screws. There's a special screw in there that looks different than the other screws. Don't use that screw. You'll just want to use one of the regular screws.
You should have 3 of those regular screws in there. But the last screw in there is just in case you lose one of the first 2. So
Oh, is it?
that's what the third one of those
Oh, okay.
screws that looks like that one. The one that's different does something.
I almost lost it.
Please don't lose the screws.
Okay, so the first thing that I'm doing to screw this down is I'm just laying the screw inside of these holes, and then I'll screw them in. Just makes it easier than doing it one at a time. So now I'm gonna screw these down. Remember, righty tighty, lefty loosey. Right to tighten, left to loosen. So I'm screwing in this one. You don't have to screw it in super tight, just until it stops turning easily. I'm gonna screw this one down. The crab is trying to get away from me. It knows what its life will be like when I completely turn my attention to it later on in the day and just continue playing with it. Okay. So once you have your battery casing screwed down to the chassis, we'll give you a few minutes just in case. Gotta make sure that those wires from the chassis are free and pointing towards you, and that these wires that are connected to the battery casing are also free. So you can see the screws are right here, and they're sitting flush with the chassis, having screwed down the battery casing. Now when you turn it over, nothing falls out, which is what you like to see.
I'll also jump in really quickly and just remind everybody that we will have the recordings of this available. So if it's going too fast or you miss a step, you'll be able to review that and kind of work at your own pace. And then there are also the written directions in the box, right, Maya and Jen?
Yes, there are. You can actually
Okay.
get them online too. So if you lose those instructions for whatever reason, they are online.
Ah, perfect. Perfect. Yeah. So just no stress. You know, if you're enjoying watching rather than watching and doing, that is perfectly fine.
So what's the next step?
So
Maya?
the next step is we're going to connect the 2 red wires together and the 2 black wires together. And so, yeah, you want to kind of group them off to the side like Jen is doing, because you'll see, if you actually turn it around so they can see it, there are these 2 holes that have metal on the top. And those will
Wait,
allow
what
from,
are these two?
yeah.
These two.
And so those will allow for electricity to go from the battery wires, which are connected to the battery, to the motor wires. So it'll allow electricity to go to the motor and allow the motor to run. So how we're going to do that is we'll take the 2 red wires. Okay. You'll want to make sure that the metal parts that are sticking out of the plastic casing around the wires touch.
So am I
And
just twisting it?
you can twist it. You can also just, also shove them in, but you just want to make sure that they touch.
Okay, so I'm gonna twist them together, sort of like those bendy straws that you can sometimes buy in like craft stores. Just twist them together, just to make sure that they are all touching. Leave no stone unturned. Okay.
Yeah, don't twist them too much because they can break.
Mhm.
And then what you're going to want to do is you're going to want to take that little part that you twisted and you're going to shove it into that hole at the back that has the metal on it, the one that's closest to the red wires.
Okay. So there's that hole down there. It's closest to these that I just twisted up. I'm going to gingerly bend the wires into the hole so that it's just resting in there.
And then what you'll want to do is you'll take one of those black battery caps. Or yes, those, the terminal caps.
Yep, so these were in the small bag.
And you're going to place it in that hole to hold in those two wires. Okay. This part is also a little bit difficult, just to get the cap in there.
So I'm just gonna smush down the wires essentially. Is that what I'm doing?
Yep, exactly.
Okay, so I'm gonna have to lift this bad boy up. Not lose.
I'll grab it.
the cap.
I will try and find that.
Okay, while Maya is doing me a favor, I'm gonna try to get the other one in. Just gonna. Okay, come on. Okay. So sometimes you gotta use a little bit of force. Squish those wires in there. Okay. So I have one on. It's pretty in there too.
Yep.
You're not gonna be able to get that thing off for sure.
No, and then you're going to do the same thing with the other one.
Were you able to find it?
I'm trying to. Somewhere in this room.
It figures I would lose the only piece that we don't have duplicates of. It sounds like something I would do. Let's see.
Yeah. While we try to find the other one, it's a good time for you guys to try to get yours on. Because it's difficult. It's probably what takes the longest out of everything to build the wire or to build the robot.
If we can't find it, we can just move on.
Yeah.
And without it, because we do have the working robot. We promise it works. Make sure that it's not.
Oh, it's okay.
Yeah. I'm glad that I moved something.
Yeah, move mine first.
Okay, thank you.
Yeah.
All right, I'm gonna do the exact same with these black wires. I'm gonna twist these up a little bit, stick them into this hole, and push them down and seal them with this cap. Okay. Twist them just so that they're touching. You don't have to tighten them too much. Okay. I'm gonna stick these. Ooh, gotta tighten them again. Gotta twist them again. Twist them a little bit more this time. Put them down into this hole. Gotta get both of those ends in there. I believe in myself. I believe hard enough will work. Okay, I'm gonna hold these back. Then I'm going to use this cap. Put that cap down and just squeeze those wires into that hole. Perfect. Sweet. I think we have both. So just to reiterate, the red wires are the power wires. And then the black wires are what we call the ground wires.
Yep.
Do you want to explain a little bit about what ground means? One of the most important concepts when you're doing this sort of work, but it's one of the hardest, I think, to explain. But I think getting you started to think about how electricity travels through wires is a good thing. Maybe that's something that you guys can look up after this. What is ground?
Yeah, it's a very important concept. It's the concept of grounding wires and grounding electricity is what allows electricity to flow. But it also helps keep you safe when there are electrical components involved in this. There's ground wires and basically anything you use. Especially there's even like grounds in, for example, the electrical sockets on the wall. There's ground holes in that to make sure that, you know, when you're plugging things in or when that your electronics are kept safe, and as well as other, you know, components that you need.
Yep, and it's important to have that ground there because if you let it, electricity will flow through you and hurt you.
Yes.
That is what ground is for. Okay.
So that does not happen. So next, one thing you're going to want to make sure is that the robot is turned off. So you'll see that there's a switch on the back.
What direction does it need to go in if you turned off? Right now it's turned, it's left.
I actually can't see which one is it on. Yes, it is left.
Oh, okay. So there is actually text up here that says off and on. Make sure that it's in the off position.
And yeah, that text is on the top part of the chassis. So it's right up here. Okay. All right. Because the next part you're going to do is you're going to put in the battery. And so the battery is what will provide the electricity for the robot. And if it's turned off, your robot will start rolling away.
Just put it in.
So you can just put it in. You want to make sure that the two sides are aligned properly, which is,
I believe like the little squiggle should go.
yes,
to
the
the
squiggle
butt.
goes there. So remember how we talked about power and ground? So batteries are the same, kind of the same way. They don't necessarily have a ground, but they do have a positive and negative side. So the positive side is the part with a little bump on it, and that would always go towards your, you know, you're on the side of your red wires. And then the flat side is your negative side, which correlates with your ground. And so you'll put that on the side that's closest to your black wires.
I'm gonna put the butt against the spring.
There we go.
Slip it in.
And then we're gonna put on the caps of battery, which you can, there's a side with the hole on it, and then there's a side with the little flat edge. You put the flat edge against the little hook side that's on the back.
So you'll see that on the battery casing, there's like a little section that has like a lip on it. This one. You want to slide the lip of the lid into just underneath the casing lip. Okay.
And then you'll want to take, actually you want to take that third screw, sorry.
I knew it was used for something.
There's usually 4 in there.
Oh yeah, there is 4 in there.
Yeah,
Okay.
there should be an extra.
So we're gonna take just another screw.
You'll take one of the other screws you should have, after you use this one, you should still have one left. That one's the one that's in case you lose it. But you'll want to screw that in.
And I'm gonna do the same thing, righty tighty.
There you go.
Just gonna tighten it so it doesn't really twist anymore. Okay,
But you
perfect.
won't want to keep tightening after it stops moving, because you could do what's called stripping your wire or stripping your screw. And that just means you wouldn't be able to turn it anymore, and it'd be really hard to get out.
Yeah, if you ever wanted to use this thing and the battery dies, you would not be able to get at the battery if you twisted the screw too much to the point where you can't actually untwist it. So don't tighten it too much.
All right. So now the next part is we're gonna put on that transparent cover. So you'll kind of see along the chassis body, there's these in the backside, there's these really small hooks.
I don't know if it's gonna show up on camera, but there's where the side with the wires, right behind the wires, there's a hook here and then a hook here.
So what you will want to do is you'll want to take the side that does not have a lip on it, so this side of the transparent cover. So there's a side that's raised on the transparent cover, which is the front side.
Right here, this is the raised side, this is the unraised
Raised side.
side.
So you want to put the unraised side underneath those hooks at the back. And then you're gonna just wanna, once you get those under there,
I believe in myself.
you'll just wanna kind of push it over the front of.
You might have to stretch it a little bit to get it to fit over
It's
the
the same
battery.
screws that you use for so the screws to put down the lid of the battery is the same one that you used to put down the casing. So it's the exact same screws.
So we don't have any extra screws.
No. I'm answering a question.
Oh, okay.
Answering the question.
You
Sorry.
have access to questions.
So, yeah, for the screw that we just put in to put on the lid, it is the same screw as,
Screw back here. I don't know if you can see it anymore.
is the same screw that you use for the side. So now what you're gonna do is you're gonna use the one screw that's different.
So this one has kind of a bigger top to it. I don't know if that's gonna show up on camera, but I have the extra screw here. It's got a smaller tip. I don't know if it's gonna show up better on the black background. No, not really. But the screw that you'll want to use for this is a little bit wider on top.
And so what this screw is for is you're gonna also take the antenna
Oh yeah, I forgot about the antenna.
and we're gonna put that on the plastic part of.
Ah, okay. So I see. So in
So-
order for it to stand up, it has that little, I don't know what you call it, like a stand.
Mhm.
And then you put the stand over this hole. Does it matter if the stand is facing out?
It doesn't matter. I feel like it's probably easier to do it if it's facing the back, because it just
Yeah.
has a little bit of extra support. But I found the easiest way to do this is if you take the screw
Mhm.
and you screw it in a little bit, and then you slide the antenna underneath it.
Okay, I'll try it. So I'm gonna put the screw that we were just talking about, the one with the bigger head on it.
Mhm.
I'm gonna put that kind of into the hole. And then
You'll kind of want to go from the side.
kind of go from the side.
You may have to turn it around in order to do it.
Nope, and you just kind of like scoop underneath it.
Yeah, there you go.
And just scoop underneath it. My antenna might be a little bit too narrow for that idea though. So what I'm gonna do is I'm gonna actually put the screw in here. Just gonna rest it inside. And then I'm gonna put it on top.
Let's say it will not stay up,
It,
but
it will not stay up, yes. But that's okay because
because that's
now
what the screw is for.
we're
So
gonna screw it in. Just gonna let it flail around for a second.
yeah, but the tighter you get it, the flatter the antenna will be. So you'll see as she's tightening the screw that the antenna kind of started leaning back towards where it's supposed to be. So you can
Okay,
tighten it a little bit,
Screwing it in.
and then you'll want to actually like rotate it towards the front once it starts getting a little bit tighter, just to make sure that it looks nice and pretty for you. But the thing about it is you can always adjust it later. It's not like,
So I'm gonna unscrew it a little bit so that I can get it rotated back to the front. I'll hold it there as I screw it in and tighten it one more time. Okay,
cool. So now it's really starting to kind of look like the crab that you want it to be. So you can also bend the antenna if you want your crab to look different. You can, it's all cosmetic. That actually, the rest of what we're doing is all just the make it look like a crab part of it. So we've kind of built already. That first half, what we did was building the parts that make the crab work, and now we're just making it look like a crab. And so the next part is you take 4 of those legs.
so these,
Yep.
Okay.
And you're gonna snap them onto one side of your butt, and you want those to be facing down.
okay, so they're kind of
Um,
like a mountain.
Yes.
And then we're gonna just push them in to each one of these 4 holes.
Yep. And they're snap fit, so you can kind of just like push them in.
Yes, okay.
It takes a little bit of pressure, and you won't
You're not gonna hurt this. thing.
you won't hurt the robot.
You're gonna be a little rough with it. That's the fun part of engineering, is being a little bit rough.
So those are built so that they're what's called snap fits. So the hole that it goes in is slightly smaller than the actual like barrel that you're pushing in. And that allows it so that when you actually get it in there, it stays instead of it just, falling out.
I believe.
But yeah, it takes a little bit of force.
And then the final one on this side. I
Yep.
think, Amy, how are we doing on time?
We're almost out of time. So, so you'll do that on one side, you'll do it again on the other, and then you'll snap on the front legs of the crab.
How are we doing on time, Amy? Sorry.
Got about 1 minute. So I think if you can get the
Okay.
legs on and
Yeah, so you can do the other side. But let's put on the claws. Yeah. Let's make at least half of this look like a crab. So you'll want to put on the crab claws with like the fake screw facing up. And you're gonna just snap it in.
Mhm.
And then when you put on the other legs and the other claw, you can turn this thing on in the back. You can see like the wheels moving maybe a little bit. Lay it down.
It won't work on yours because it's not resting on the thing. But
Right. But once you get yours in, should be good.
all right.
Any questions?
thank you guys. For students, if you are still working, no stress. This is something that you can definitely continue through the weekend. You can tinker with it, work on it, play around with it. We have also included in kits some googly eyes. That is purely cosmetic, but in case you wanted to give your crab a little more life, you can add on some eyes to it. And make it truly your own. These are your robot crabs to keep and use and play around with however you'd like. So we're gonna take a break, but as Jen and Maya keep working, we'll leave this screen up. But at 10:50, I will pull our biomedical engineering presenters over and we'll begin the biomedical engineering session. So if you're at like a good stopping point right now and you want to start putting your crab robots away, this is a good opportunity to do that. If you want to finalize some pieces, you have about 3 minutes. Jen and Maya will also stay, I think, logged in. And if you have any questions, you can throw them in the chat. But again, 3 minutes. And if you need like a quick break or just time to stand up and stretch, this is a great time to do that. Oh my gosh, it's so cute.
You didn't push it all the way down.
I'll bring it closer so you guys can actually see it. Try to walk off, but it won't. It's got edge detection. Haha! Does the other one work now?
All right, everybody, it is 10:50. We're gonna get rolling into our final session. Again, a huge thank you to Jen and Maya from the Chrome Lab and Dr. Gorlowicz earlier. Truly hope everybody enjoys having a little robot of your own. And if you, as you play around with it and look at the inner workings of it, hopefully you learn something a little new about how about robotics and about some various opportunities in engineering. Now, though, we are going to turn our attention more to the medical field. So I have with us Dr. Case, and she's going to introduce biomedical engineering and talk about some of the various applications there. So Dr. Case, when you are ready, you can take it away.
Sorry about that. Good morning, everyone. We are so excited to have you participating today in our introduction to various types of engineering. I am going to share my screen. I have a few slides, and then we're actually going to do our We're going to talk first about biomedical engineering, introduce it to you if you haven't heard of this area before, and then we're actually going to give you a chance. One thing I thought that maybe students would enjoy today is a chance to ask students who are actually studying, in this case, biomedical engineering, but you could ask them generally about what's it like to be an undergraduate student studying engineering or even a graduate student. So we're going to have a short student panel so you can actually just ask some questions about pick the brains of a couple of our students from our program to throw out any question that you'd like. And then we're going to talk a little bit about a design challenge where we have sent kits to your schools that have various components in them with the idea of trying to make some sort of prosthetic hand or limb. And we'll talk a little bit about
On just a second, guys. I think we might have a technical difficulty here. Just stand by. All right, there's Dr. Case. And you're on mute, just a heads up.
Can you still see my screen though?
No, you'll need to reshare.
All right, share again. Okay. Sorry about that. Yeah, I totally forgot to switch over to my Ethernet connection on my notebook. So occasionally that happens, even in my office at SLU. So it's
all good. It's just one of the fun adventures in our virtual
yes.
here.
All right. So I was trying to share with you that I had actually, when I went to undergraduate and was choosing where to go and what to major in, it was actually before the internet and everything was on paper. And so I had seen lists of majors and I saw biomedical engineering, and I had really enjoyed like a life science course that I had in middle school, and had enjoyed sort of my math and science courses in high school, and had really had a high school professor or teacher who had said, go into engineering. Like he was really pushing a lot of students to go into engineering. So I kind of did the same sort of event that you were at today at a school, at college where I lived in Oklahoma, and thought maybe engineering would be a good option. So what as biomedical engineers do we do? Or do we study? The interesting thing about biomedical engineering is that it's really a discipline that's at the edge of engineering, biology, and medicine. And really the overall goal with whatever we're doing, whatever we're studying, is to improve human health. It's really fun because we get to work at this boundary of multiple different disciplines, not just engineering, but also the biological sciences. Sometimes that includes chemistry, biochemistry, can include physics and biophysics. And really this is so that, again, the overall goal is in whatever we do to have a deeper understanding of how the human body works and ultimately to improve human health. And we're doing that by working with others, working with clinicians, working with companies so that we can improve treatment. And this was kind of the overall definition by the Whitaker Foundation. The Whitaker Foundation was really instrumental in the 1990s and 2000s in funding new BME programs and funding graduate students and faculty members, I actually had a Whitaker Foundation graduate fellowship for my PhD work. So biomedical engineering. Biomedical engineers are people who help design artificial heart valves, shown here. This is a bileaflet mechanical heart valve. Biomedical engineers help improve imaging techniques. So here we can use a non-invasive imaging technique to detect a tumor growing in someone's brain, right? Non-invasively. Biomedical engineers help design hip and knee replacements. So this is part of a hip replacement. So if the cartilage at the end of your femur, this region is called the acetabulum, this rounded region, starts to wear out, if you end up with something known as osteoarthritis and you're in pain and you can't move around very well, then sometimes the best treatment for you is to actually replace your bone and cartilage, your joint in that region with a prosthetic. So these are just 3 examples of what a biomedical engineer might help design to improve human health. If we think about a little bit more the traditional areas of engineering, electrical engineering, mechanical engineering, chemical engineering, biomedical engineers really need to have knowledge from all of these areas, plus knowledge about biology and medicine in order to study various things about the human body or to develop technology, both diagnostic and therapeutic, that will allow us to improve human health. So some people study more the human body as a system, as a machine almost. We can study or individual tissues within that body. That's kind of the area of biomechanics. We can design new materials to be used in an implant in the body. When we think about that prosthetic hand, we may think about some use of biomaterials there. If I wanted to have a prosthetic hand that looked more like a regular hand, I'd need something on the outside that looks kind of like skin. Bioinstrumentation, these can be, again, things that help with diagnosis, like some of those imaging techniques, but they can also be internal sensors. There are people who have implanted devices that either help pace their hearts, so those are called pacemakers. Some people have implanted glucose sensors and glucose pumps so that they can receive insulin. Rather than having to have injections, they can receive insulin sort of continuously or on an as-needed basis. I've already mentioned imaging, brain-computer interfaces. This is getting into some really sophisticated new areas. So how do we help people who have various disabilities? If you have a neurodegenerative disease and you're in a wheelchair, maybe you can't even move your arms, but you still have an ability to do, your brain is still very active. How might you improve your ability to live independently on your own, or at least partially independently? People who actually have lost the ability to speak, either due to a stroke or again, neurodegenerative disease. Are there ways that we can help improve their ability to communicate? And so you've probably seen pictures of this on the news or in various places of people maybe being able to use their eyes to manipulate kind of a cursor to touch individual letters and then form words, but that's a really slow process. We're trying to think about more sophisticated ways that will lead to much faster levels of communication that might eventually get to the level of how our actual brain works. And then with rehabilitation engineering, and that's going to cover a lot of different things. Prosthetics would fall underneath that, but again, helping people who've had sort of severe trauma or severe injuries improve. Our prosthetic hand that we would think about would fall into that area. And then medical robotics, this is a really cool area. When we think about surgeries, right, we think about individual surgeons doing, working with their hands to do various things inside a person's body. But right, with humans, our hands get tired, our backs get tired, our minds get tired. There may be ways that we can use robots and the precision, right, and the lack of fatigue that a robot would have to improve some of our surgeries. So one of the surgeries that a professor here at SLU is interested in improving is a spinal surgery. So it's a really tough surgery. It takes a really long time. It's really hard to see like where you're headed to on a vertebrae. And so they've been using this robotic arm that's actually used for automotive in the automotive industry, but thinking, could we adapt that robotic arm to be used for some sort of type of spine surgery? So that's kind of an overview of a lot of the general areas. I'm going to highlight tissue engineering in a minute, because that happens to be one of my specialties and what a variety of the professors here at SLU do. But I wanted to also give you an idea, well, great, that's what biomedical engineers do. But more generally, if you get a biomedical engineering undergraduate degree, what would you typically do with that degree? So you could go work in industry, and I'm going to highlight that piece of it because that's kind of really new and different and exciting. You can get a job directly out of having your undergraduate degree in biomedical engineering. So we'll look at that a little more carefully. But you can also, if you really enjoy the topic, and if you really enjoy the idea of doing sort of research in a lab, then you might want to go into graduate school and get a master's degree or a PhD, and you'll get a chance to talk to some of those graduate students doing that in our program during the panel. And then a lot of times, the majority of those students then go on to industry, but they first choose to get an advanced degree in biomedical engineering, or sometimes in a related biomedical science, or maybe in another engineering, depending on where they really see their career going. But you can also go to medical school. That's a very common track for students who take our degree. About maybe 20 to 30% of our students in our program end up going to medical school, but you actually could also go to law school. So some people could take their technical knowledge on the engineering side and go do patent law, or go do law related to the FDA or to companies, or you could even go to business school. So some biomedical engineers really just get excited about starting new companies and how that process works. And those are called startup companies. And that's where we often see our people, some of our biomedical engineers working. So just one quick highlight, I won't spend too long on this, but one of my particular areas of interest is tissue engineering. And so I think this may or may not be one that some of you, I think if you're in high school, you've probably seen this before. But with tissue engineering, what we're really trying to do is to both combine principles from engineering and the life sciences to develop tissues and organs that we can truly transplant. So grow them in the research lab, or really eventually a clinical lab, to then transplant back to a patient so that we can maintain, restore, and improve the function of various tissues and organs. And so this idea has really been around at this point for roughly, what, 25 years? No, 35 years, wow. And we've, the general idea is that we take cells, we need to put them into a 3D space because most of our tissues are 3D in nature. Skin is a little more planar, more of a 2D type structure, but a lot of our tissues have a thickness that we need to think about. Certainly if you thought about something like a liver, that's a very large organ that would definitely be 3D. So we want to take cells and we combine them with what we call a template or a scaffold that allows us to position the cells into 3D space. And then we often give them some sort of what we call signals through kind of the nutrients that we provide to the cells so that we can help get the cells to produce extracellular matrix proteins, and those proteins and other factors get combined into what we think of as actual living tissues. So here's an example shown here of a tissue that I actually grew. These were stem cells that come from bone marrow. I gave them signals to make them become chondrocyte cells, the cells that are in your cartilage, and the reddish color shows you the matrix that they lay down on the template. The template here is actually the whitish color. And here was a very famous image that at the time the internet was very new, and so this went probably viral at the time, this idea of this mouse that had an ear growing on its back. So this was a mouse where the researchers in the Vacanti lab had put in a scaffold in the shape of an ear underneath the surface of the skin of this mouse, and they were able to grow cartilage on it. Oops. I wonder what happened. I seem to be missing something that I was expecting. Let me go back a minute. Oh, goodness. Here, let me get out for just a second and see. Somehow it jumped down. Oh, wonder why. That's not showing up. It's weird. Oh, well, I don't know how to fix that. For some reason, a few of my slides seem to be marked off and they're in my queue, but they're not showing up. So that's really weird. Can you see it this way? Can you see it says career opportunities industry?
Yes. Yeah.
Okay, then I just won't put it into the slide mode. Sorry about that. Yeah, I have no idea. Like I inherited this from somebody else and made some changes, but Yeah, that's why I was missing my industry slide. I know I'm going on a little bit long, so let me wrap it up here with this idea of industry. So again, you can get a degree in biomedical engineering, 4 years of undergraduate studies, and go into a job directly in industry. And in 2018, there were about 20,000 jobs in biomedical engineering in the United States, and the pay was about $89,000. So this is starting pay for someone with an undergraduate degree in biomedical engineering. So that's pretty good. Biomedical engineers, when they work in companies, they can work in a variety of areas in research and development. So that makes sense in terms of thinking of new products. In manufacturing, once you have an established design, you want to make sure that the product that you're manufacturing, right, is done consistently, is done well, how you do that process efficiently. And then part of the, are you doing it the right way every time, is the quality control piece. That companies need to hire people to work in quality control, but they also need to hire people to work in regulatory affairs. And these would be people who interface with the FDA, the Food and Drug Administration, the people, the FDA makes sure that they keep us safe, that companies are checking that they're doing everything correct in terms of manufacturing, that their products are dependable, things like that. And so companies need to have people with often a business or an engineering background to work in regulatory affairs. And then if we think about the products that companies make, if in the realm of biomedical engineering, who we really sell the products to? We don't sell them to patients. We actually, these products would be sold usually to hospitals or to clinicians or to surgeons who use them. And so there are also opportunities to work kind of indirectly in biomedical engineering, or take your engineering degree and then go work in sales or in clinical education, where you're really working in hospitals, talking to, or in clinics, talking to actual physicians and surgeons who are going to use your product to make sure they're using it appropriately, to identify any problems that they're seeing, to help your company continue to develop their product, advance their product, come up with new ideas. And the cool thing about this, and this would be true of any engineering area, you could go work for a variety of companies. Some are very large and established companies. You've probably heard of companies like Medtronic or Johnson & Johnson. We have moderately sized companies. So they've been around for a while, but they just are focused on a smaller number of products. We have a company here in St. Louis called Biomedical, although I think they've been acquired by somebody else, but I'm going to stick with that name. Stryker is a company who does hip and knee implants. And then maybe you actually really want to go work for a very small company. You just want to work in a new and exciting area. Then startup companies are an option for you in biomedical engineering, as well as other engineerings as well. And some of these startups actually exist in St. Louis. There's a pretty strong group of entrepreneurs and entrepreneurial people here in St. Louis in a variety of areas of engineering. And then the other thing to consider is that you could also go work for a government agency. So the National Institutes of Health, the FDA, VA hospitals, NASA, Department of Defense would all be people who would need to hire some biomedical engineers. So why don't I stop there and we switch over to the panel, because I want to give students a chance to ask some questions of our graduate students. So today we have Allison Paoli, we have Alyssa Brown, and we have Sam. Well, actually, is it Sam or is it Joey? I need to go back and see.
I think Sam is coming over.
And Sam Steely, who are all graduate students in our biomedical engineering program. Alyssa and Allison are students who did both their undergraduate degree here, and now they're doing a master's degree, and they're both getting ready to finish this spring. And then Sam is a PhD student. He did his undergraduate at Milwaukee. He can give you the full name, I'm blanking on it. And he's
Milwaukee School of Engineering.
Milwaukee School of Engineering, and then he came here to work on his PhD. And so he's in year 3 or year 4 at this point? Year 4, and maybe about a year, half a year to a year from finishing. So I'm going to turn it over to all of you, to you students, to ask some questions of these panelists.
Great. Dr. Case, if you wouldn't mind stopping your screen share.
Yes. Oh, yes, of course.
And then, yes, for our middle school and high school students, if you have some questions, feel free to put those in the chat. I'm going to jump in and get us started if Allie, if you would start us off with just a brief introduction of yourself, why you chose biomedical engineering, maybe your career goals. We'll go Allie, and then Alyssa, and then Sam.
Hey, hi guys. So my name is Allie. I'm from Chicago suburbs area, Plainfield, if anyone's familiar. As Dr. Kay said, I am in the 5-year bachelor's master's program at SLU. So it's basically 5 years total. You finish up your bachelor's and then you do basically an additional year for your master's. I am currently doing research in basically tissue engineering, so muscle regeneration for like large scale muscle injuries, and basically doing some like stem cell research with that. I'm not going to get too in depth with it. I originally chose biomedical engineering because I was really interested in like medical devices and prosthetics, but now my interests have kind of shifted a little bit towards tissue engineering. And I also did complete a minor in mechanical engineering during my undergrad. So got a little bit of background in that. And yeah, career goals. I am still looking for a job right now. I'm kind of all over the place with it, trying to figure out where exactly my interests lie career-wise, but just kind of interviewing with some companies, looking a little bit into medical devices right now. So.
Right, so I'm Alyssa. I'm also from Chicago suburbs. I'm from St. Charles, but was actually born in Plainfield, which is really funny. So, but yeah, so like Dr. Kay said, I did the exact same program as Allie. I did my undergrad here. I also have a minor in mechanical engineering, and then I continued as a master's student for year 5. My research, I'm actually in Dr. Kay's lab, and I'm focusing more on mechanical side of things. So how, and like fracture callus healing, so fractures or broken bones, and the process of potentially accelerating or speeding up that healing process through sound waves. So that's where my area of research lies. My interests are more mechanical. I definitely want to work on potentially fluid dynamics, or I realized I was talking into the wrong ear. I'm so sorry. I can restart if you want me to, but anyway, yeah, so my interests fall more in fluid dynamics or more mechanical side of things, so like prosthetics and stuff like that. Same with Allie, still looking for a job, but really looking forward to getting out into the industry and working on some really cool projects. Yeah, again, sorry about my mic. I forgot which one it was on.
Yeah, so I'm, like Dr. Kay said, I'm Sam Steely. I'm a 4th-year PhD student. I'm originally from St. Louis. Like she said, I went to Milwaukee School of Engineering for my undergrad. I completed a degree in biomolecular engineering, which is similar to chemical engineering. And at SLU, my research mostly focuses on drug delivery and using different materials to kind of optimize delivery of different biologics to the body. After graduation, I'm planning on going into industry. Not really sure where yet, since I've got another year and a half.
Wonderful. Thank you guys. Again, for our students and teachers watching, feel free to submit any questions to the chat. But if you guys would all entertain me, like think back to many, many years ago while you were a high school student and you were starting to think about, okay, what do I want to do with my career? Do I want to go to college? What am I going to study? So if you kind of think back to that point in time, could you talk us through like where you were in your how you thought of engineering, what you knew about it, and then maybe some advice for our students joining us today who, you know, today might be the first time they've heard about engineering. Maybe they are thinking about that career. So just kind of any advice or any viewpoints in that arena.
Yeah, definitely. So back in high school, I didn't really know what I wanted to do at all. My brother, I have an older brother, he was mechanical engineering. So he had done the whole mechanical engineering. I knew about engineering. My dad works with engineers, so I knew that that was a thing, but I actually thought that I didn't want to be an engineer. I was like, no, that sounds boring. I don't want to do what my dad works with. I don't want to do what my brother does. I want to do something different. So I knew I wanted to do something in the medical field. I always loved biology, but I also really, really loved math. I That was always my favorite subject in school. I loved it, and I loved bio. I loved science. I knew I didn't want to go into any, like, I didn't want to go into business. I didn't want to do English or like anything like that. So I was actually on a college visit for my brother, because my parents had me go on the college visits with my older brother. So I was a freshman, and I actually came to SLU because he was looking at SLU too. He didn't go here, but I ended up going here, which is kind of funny. But I was on a visit, and our tour guide was BME, because we got connected with an engineer because my brother was going into engineering. And he was talking about BME and how he was actually pre-med, on the pre-med track, but studying biomedical engineering. And I was like, I had no idea what BME was. So I talked to him a lot about what BME does, how it's kind of a combination of all of the things that Dr. K said: physics, chemistry, bio, math, all of that stuff. And I kind of was super hooked. So then I went home and looked it up, talked to more people, and figured out, okay, I kind of want to be a doctor, so I'll go into the pre-med track, and then as my undergrad, I'll do BME. But then as I studied BME more and more in undergrad, my sophomore year, I was like, okay, I actually really love this industry. I love this major. I love all the potential options that I can do once I get into industry. And so I actually dropped the pre-med track, picked up my mechanical minor, and focused more on preparing myself for industry rather than pre-med, or medical school. So I kind of started one way and then was like, actually, I love this, so I'm gonna stick with it. But yeah, that was kind of my journey with how I got into this major. I don't know if anyone else wants to talk about it.
I can briefly, just because I feel like I had like a little bit of like a different path. So my sister also was a mechanical engineer, and she was finishing up her school when I was starting to apply. I wasn't really super into mechanical and kind of like took engineering out of my sights because of that same kind of thing. But my senior year, I was taking an anatomy and physiology class, and my teacher then showed me a video all about like prosthetic design, and just like it kind of was like a brief intro into like all the different like categories of biomedical engineering. And I ended up talking to one of my physics professors about it, and he kind of was like, this just sounds like something that you'd be really interested in. And I was always kind of on the path of wanting to go straight into industry. But yeah, I mostly chose it also after seeing my sister. She got a lot of opportunities purely for being a girl in engineering, which I think is really different than most other fields. Like a lot of really male dominated fields, you're not going to get, like, it's like harder to get a lot of opportunities. And it's, I've just noticed that engineering is one field where you actually do get some more opportunities sometimes because you're a girl, you stand out a little bit more. It's something that a lot of companies in the industry are trying to pull more girls in. So it's been great so far. I know it's really beneficial for getting into very like engineering focused schools. Like she got a lot of opportunities and a lot of scholarships, mostly for being a girl. It's one thing that made me really interested, is something that I think it's like really cool to get into a field and like be part of like the growing population of girls within it. So that's kind of one thing that really pushed me into it.
Yeah, and for me, I just liked science a lot in high school and wasn't really sure where that was going to take me. I ended up taking an engineering class, kind of a basic engineering class in high school, and kind of combined those interests and decided I wanted to do engineering. So I didn't have any engineering background in my family or friends or anything like that. It was kind of just a leap for me.
Wonderful. Thank you, guys. My last question before handing it back to Dr. Case, kind of like a rapid fire question, but what's been the most surprising or the coolest thing that you've gotten to do in your biomedical engineering education?
I can start. My coolest thing was my research. I love doing research. I never expected to be like as hands-on as I've been able to be. I was able to do undergraduate research and then now obviously my graduate research. And it's been like something that I think has really been like super fun and like made my classes actually like applicable to something that I'm doing hands-on.
Yeah, same for me. It's definitely my research. So one of the projects I'm involved in is working with a professor on the medical campus that delivers an enzyme to children with this very specific rare disease. And so I'm able to see a direct link between my research and how it can actually help somebody, especially a child's life.
So for me, I think obviously my research is really cool, but to say something else, and another opportunity that I was able to get a part of, become a part of at SLU, was actually Engineers Without Borders. So that's a club for undergrad and grad and professional people. So there's like, you can be in it through all stages of your career and education. And so that's basically an organization that really focuses on engineering solutions for developing countries. And so that was one of the coolest things that I was able to be a part of at SLU because of the fact that I was able to actually work on, it wasn't really, I mean, it is kind of BME related, but it was more civil. So we were making a water distribution system for a community in Kenya, actually. And I just really loved being able to work with the community, having to ask them and figure out like what the best solution for them was going to be. So it was using a lot of the engineering skills that I've picked up throughout my schooling to actually help a real life community. And that project is still ongoing. If you come to SLU, you can always be a part of it. It's a very, very lengthy project. But yeah, so that was probably one of the coolest things. You can be in that club if you, regardless of what major you go into. But yeah, that was really cool too.
So great. Thank you all for your insights. I hope our students watching kind of took away, I mean, I got your enthusiasm and your excitement to help other people as some of your motivation in this career field. So we know you're going to do awesome things moving forward. And thank you so much for your time. So Dr. Case, I'll hand it back to you for about our final 5 minutes. And
all right,
we'll go from there.
So let me jump down. I wanted to briefly, we have sent kits to all of your schools. There's supposed to be enough for everyone to have their own individual kit. And let me jump down. We can come back to this other slide in a minute. But the idea is that we're going to have you make some sort of, from the items that are in your kit, to have you try to design and fabricate some sort of prosthetic hand or gripper, something that you could actually use one person to transport objects. Now, if we think about this idea that, you know, for a very long time, humans have been getting into, you know, unfortunate accidents and whether it's dealing with some sort of predator or in warfare, various things, we have lost, right? Humans for a long time have lost various limbs. And so if we go all the way back, we can see examples from ancient Egypt, and then more recently in Rome of solutions to missing limbs. So in Egypt, they were making prosthetic toes. There are examples of prosthetic toes made out of wood and leather. In Rome, they made a leg replacement for them out of bronze. I think we can all also relate to the idea, right, from various movies and the stories that we read growing up of, right, the pirate's hook as being, right, that's truly a type of prosthetic to replace a hand and part of an arm that someone had lost. Now, it was really in World War II and all of the wounds, right, and trauma that soldiers had experienced, leading to many lost limbs, that really there was sort of a renaissance in the design of prosthetic limbs. So both upper limbs and lower limbs. And so those were starting to be made out of wood, like a variety of materials, wood, metals, and leather, although these are still fairly traditional types of materials that would be used for you know, a variety of clothing and just kind of traditionally used for various needs that humans had. It was really in, say, 40 to 50 years ago with the advent of really plastics and various types of polymer chemistry that we began to have more sophisticated approaches that we could have for prosthetic limb design, where we started using materials that were softer, more malleable, could be fabricated in a variety of ways. And so we were able to start, making actually shapes that looked like true hands, that could fit over a stump of an arm, or the same way with the leg. And now we've really moved on to much more sophisticated prosthetic limb designs. And if you've watched the Olympics, you may have seen some examples of this with these running blades that some very elite athletes are using now. Here's an example of a hand that is actually going to be able to move individual fingers, and the idea of starting to include sensors in the fingers for actually being able to have tactile sensations. And so these are a couple of links that you can have, but I wanted to very briefly mention my own personal experience at SLU. We have an employee here at SLU, his name's Andrew Oberly, and he was actually a graduate student who in the summer of 2012 was studying abroad, doing research on chimpanzees in South Africa, and was unfortunately attacked and viciously mauled by those chimpanzees and nearly lost his life. He had severe damage to his face. He lost almost all of one hand and damage to another, and a variety of other wounds. After they had gotten him stabilized in Africa, they were able to bring him back to SLU, and with the help of a variety of surgeons here, start to help sort of heal his body. And Andrew is an amazing person. I was able to meet him, I think my first or second year at SLU, and he actually brought his prosthetic hand, and I got to shake his prosthetic hand. But Andrew has really is helping companies kind of develop advanced prosthetics in terms of being someone who uses their products, but also he's very much about wanting to give back and to help others who have been exposed to trauma from a really holistic approach, not just on the physical side, but on kind of the spiritual and mental and emotional side as well. And so there's almost 30-minute video that you could watch if you want to go to this website. We'll have, I think, this up later for the link. We didn't have time to look at it today, but his story is really kind of an amazing story. He's an amazing individual. And so when I think about prosthetics, I always think about Andrew and how I got to see a video of him working with one of the prosthetics and kind of a second generation, and still seeing kind of the challenges of having a hand prosthetic that can truly begin to function like a human hand. So what we have sent you in your packets, again, we are asking you to take some time, and we would sort of suggest maybe limiting this process to about 20 minutes to where you design and fabricate something that will act as a prosthetic gripper or a hand. It should be designed so that one single person can use it to pick up and transport items. You should only use the items included in your kit, along with some glue and tape and scissors. With the string, don't use the string to wrap it around the items, but you can use it to kind of connect other items. And with the tape, we're really thinking of using the tape only as a way to create grip, not to use it again to stick a bunch of items together. We hope that you will enjoy this challenge. We are asking, I think in the instructions we've included in the kit, we're asking you to send us your images of the designs you come up with. We're going to be sending some follow-up questions to your teachers, as well as maybe a list of items to have you try to pick up. But I didn't want to give you the items in advance because that might, I think, tip you off too much in terms of what you should try to design. So try to think about being able to pick up both larger and smaller items when you're designing your gripper or your hand. I hope you have enjoyed getting to learn a little bit about biomedical engineering as well as some of the other areas of engineering today. We certainly enjoyed our opportunity to speak to you today.
Thank you so much, Dr. Case. Yes, in our final minute, that quick reminder to please complete that activity kit on your own. If you want to work in groups, or if it's something that you want to take on this weekend, it is a fun activity to kind of think outside the box, think of materials in a different way. And we would love to see what you create for your prosthetic hand. You can send us a picture or a video at parksevents@slu.edu. But once again, a big thank you to Dr. Case, our panelist from Biomedical Engineering. Engineering, as well as our presenters from the Water Institute and the Chrome Lab today. We greatly appreciate all of them sharing their time and expertise to teach us about engineering and the opportunities that exist in the field. We would also like to send a thank you to the American Association of University Women. Their funding made our activities possible today, so each of you are hopefully able to take home a little something from our time together. And finally, a huge thank you to all of our attendees. So middle school and high school students, teachers, thank you incredibly for joining us today to learn more about engineering. We really do hope that you enjoyed the activities. You learned about some careers open to you in the industry that you hadn't previously known about, and you're excited to find out more about opportunities in engineering available to you. I will say at St. Louis University, we have a series of summer camps that are open to various levels of high school students. So if you enjoyed some of the content and the presentations today, I do encourage you to check out the summer programs. I will send a link to all of your teachers. We have a civil engineering camp, a robotics camp, an overnight engineering academy, and an overnight aviation academy. And so if you are interested, again, we encourage you to apply for those. Our applications will stay open through March 13th. Our session today has been recorded and it will be posted to our YouTube page. And again, I will email out that link when it becomes available. And that brings us to the end of our virtual Introduce a Girl to Engineering Day virtual field trip. We hope that in the future, when it's safe, those of you in the St. Louis area, if you'll come visit us on SLU's campus to learn more about our engineering programs, meet us in person, and get to see some of our lab spaces. In the meantime, please don't hesitate to reach out to us at parksevents@slu.edu to connect further. Thank you again. I apologize for going 1 minute over. Have a great rest of your day and a great weekend. Bye-bye.